it's kind of Zoom and the person has stabilized. So I'm very happy to have Cole back again and give us the second half of this lecture series. I should say that one of the reasons we chose to have a shorter day is, I think one of the benefits to in-person conferences is that you can actually talk to people about actual mathematics. So, take the opportunity to reach out to somebody today, talk about math, and also to explore the beautiful city of Toronto. All right. Well, take it away, Cole. I'm very excited.
Okay. Thank you very much. Again, very happy to be here on a second day. So yesterday, we took a look at shock formation in an inviscid model in the Euler equations, the compressible Euler equations. And to kind of close out the day with a generous amount of hand waving, I argued that the kind of generic structure of an incipient new shock forming in the midst of a gas should be dominated by a certain cubic structure. So I wanted to write that down again. So this is a notion of generic shock formation, and it should be dominated by a profile solving an inverse cubic equation. And I've called this profile theta bar, bar indicating that it's some kind of nice exact model solution. And I was using theta to refer to the solution of a scalar conservation law. So this is satisfying an inverse cubic problem, and I want to point out some things. So this is designed to form a new singularity, a gradient catastrophe at the origin in space-time. And I've shifted all my coordinates around to arrange that, and I've also shifted the value of my unknown theta so that the new singularity forms at the value theta bar equals 0. So that's kind of a whole bunch of nice normalization things to simplify the notation a bit. And we have here the derivative of the advection in the scalar conservation law at 0, where this new shock is forming. And the key point is that this derivative should be non-zero, and in the normalization I'll work with, I'll assume that it's positive. That's just an arbitrary choice. And this reflects the hypothesis of genuine nonlinearity. And let's see, then there's this other coefficient, beta, which governs basically how stretched out the cubic is. This is something that depends on the initial data. So this is, I'm taking it also to be a positive number. And if you're thinking through this carefully and getting a bit puzzled by the signs, it can be helpful to bear in mind that because my new shock is forming at the origin in space-time, and I'm thinking about the lead up to that catastrophe, all my times t are negative. So I'm working in the past here, and this should mean that this gives a smooth cubic expression when t is strictly negative that then forms a cusp when t is equal to 0, reflecting that gradient catastrophe. And so I argue that this is the generic structure for genuinely nonlinear shock formation in a scalar conservation law. Now, of course, Euler is a system, but the setting we were exploring yesterday involved solutions of the compressible Euler equations that are near so-called simple waves, which satisfy a scalar conservation law. And therefore, there's kind of there's a background nearby scalar conservation law that we're thinking about there. And in general, a solution of the Euler equation of that full system. So for systems, I'll state this a bit loosely. I'm glossing over a bit of detail of exactly how you measure things. But one should expect that one component that I'll call the shocking component of your system resembles theta bar, and the others should be much smaller near the origin, meaning the dominant behavior close to the origin is concentrated in one component, the one that is developing a shock. And so, again, there's a bit of subtlety in exactly how much smaller depending on exactly how you choose to measure this, but in the kind of simplest possible way of measuring this, you're no larger than theta bar squared. Recalling that theta bar is vanishing at the origin, so this is a much smaller quantity than that shocking characteristic. So this is what we should see for Euler. And that's basically where I want to leave off the inviscid analysis. I've kind of brought it more or less to a complete point for my next task, which is to think about what happens when I introduce some viscosity to the problem. So I'm transitioning from the compressible Euler equations to the compressible Navier-Stokes equations with viscosity. And I want to think about how does viscosity, let's say, interfere with the shock formation process, particularly when the viscosity is relatively small. So to get into that, of course, I need to write down a viscous model. So let me start off by just recalling Euler, which will give us the left side of our Navier-Stokes problem. So the way I chose to formulate it is in terms of three state variables: mass density, momentum density, and energy density. And one can express this in the form of a conservation law. And typically speaking, the quantities in the conservation law are being advected by a velocity u, which is just the velocity of the fluid, and it's given by the ratio between the momentum density and the mass density. And then you also have additional forces in the gas coming from the pressure, which also have energetic consequences, so that shows up in both the momentum and energy equations. And the pressure is implicitly defined as a function of rho, m, and e through some equation of state, which I won't be writing down in detail. There are many common examples out there. For example, if you're studying a monatomic gas or a more general polytropic gas, then there are some relatively simple expressions for P. But the details of the expression won't matter for me. So I'll kind of leave that indefinite. The main point is just that although it may not explicitly look like it, everything in this big parenthesis is an actual function of the state variables written here. So this is a closed equation. And for Euler, we would have 0 on the right side. But now I want to introduce additional forces into the system, which reflect friction. And it's a bit more difficult to derive the structure of these forces from first principles. So one approach one can take is to take the viewpoint that your compressible gas is in some sense a limit of an underlying mesoscopic kinetic model, like the Boltzmann equation, for example. And then you could study, if you take the Boltzmann equation and send something called the Knudsen number to 0, at leading order, you'll get the compressible Euler equations. And then you could ask, what's the first corrector to those equations that would come from the underlying collision dynamics of your kinetic model, which again might have something to do with some friction effect at the macroscopic level. And if you do that, you'll extract the Navier-Stokes correction with a small prefactor, which actually is given by the Knudsen number, although I will denote it by nu, just because I'm too familiar with this, although this expression will look a bit odd if you're really a serious fluid dynamicist. So really I should be calling this epsilon or something, or kappa for Knudsen, but alas. Okay, so there's a number of new letters involved here, and I'll try to go through them one by one to give you a bit of a picture of what's going on. So this nu for me is just a small parameter, positive. And it again reflects the Knudsen number. And actually, in order to rigorously derive this as a corrector to compressible Euler from a kinetic equation, it's necessary that this be small. That would arise only in a certain asymptotic limit when you're sending this to 0. So this is something that I didn't really appreciate until recently, which is that the compressible Navier-Stokes equations to my understanding, do not have a kind of well-founded physical derivation for fixed positive, say, unit scale nu. They sort of only have a significance when nu is in a limit tending to 0. And that's the one we'll be considering today. That stands in contrast to the incompressible Navier-Stokes equations, which can be derived from first principles to have a unit viscosity from kinetic equations under a different scaling. Okay, so enough about that. And then we have certain terms, we have certain viscous terms acting in the different equations. Crucially, we have nothing acting in the mass conservation equation. So there's no kind of diffusion of mass, and this actually leads to loads of mathematical challenges because it means that the diffusion we've added is degenerate. It doesn't act on one of the components of our system. So we're not in a kind of uniformly parabolic setting. This actually will not be a big issue for the analysis that I'll talk about today, but it is something that kind of arises constantly in the theory. And then in the momentum equation, we have probably the most familiar form. We basically have, I'm missing a derivative here, excuse me. These should be second order, so I'm missing a derivative out front. We basically have a second order derivative of the velocity, like you would expect to see in kind of a parabolic problem, and it has a certain coefficient mu out here. And let me make sure I get the language right. Yeah, so mu is what's called the dynamic viscosity in fluid mechanics. And one can take it to be constant. It's not really necessary for the analysis I'll lay out. So more generally, you'll find that it's, again, some function of the state variables. Really, it's a function of the temperature of the gas. But the temperature itself is some implicit expression of these variables that, again, comes from some equation of state. And then in the third equation, we have another expression involving mu, now quadratic in u, which makes some sense because we're dealing with an energy, a quadratic expression of u in the kinetic energy. And then there's a thermal term as well. So here, this capital T is that temperature, which is, again, implicitly a function of rho, m, and e, and kappa, the thermal conductivity of the gas, is also implicitly a function of temperature. I won't specify further what they are. There are various expressions one can get from certain Boltzmann limits. They contain information about the collision kernel that you're using in the underlying kinetic equation if you're trying to derive this from that perspective. But their explicit forms are not of terrible importance here. So I wanted to lay that out, but it's the last time that I'll make use of this explicit formulation of compressible Navier-Stokes. So as with Euler, I'm going to abstract things and just view this as an example of a more general framework for some viscous conservation law. So I'm grouping everything into a vector valued variable psi, like last time. We have a nonlinear flux of psi on the left, as with Euler, and then on the right, I'm just going to express this as this small constant nu times a second order but nonlinear term, which I'll write like this. And so now B of psi is basically representing all the coefficients contained in the Navier-Stokes expression. And this is our diffusion matrix. So one can check that it's at least non-negative definite, which it had better be if you have any hope of this thing being well-posed, locally well-posed. But it's important to bear in mind that it is not strictly positive definite. It has kernel just arising from that first component, the rho component of our equation.
Is there a reason for first principles why this first correction is perfect divergence?
I believe it's because you should still maintain the conservation of these quantities. Yeah. So so it should go away upon integration. So I'd actually expect, although maybe I shouldn't be too aggressive in stating this, but I would expect all the corrections to have a divergence out front. Let's see. And as with last time, I will also often rewrite this first order term as some matrix A, the advection matrix, times the spatial derivative of psi, which just comes from taking the derivative of this vector valued function f. So you get a matrix there, the total derivative there. So a few comments. Again, kind of the perspective I took last time in the inviscid problem was to view Euler as an example of this more general system that happens to have a few nice properties, and to recall those properties when we need them, but otherwise to generally work with the general framework. And that's the same thing I'm going to do today. So I'm going to focus on this more general viscous conservation law, and from time to time it'll be helpful to state that B has some properties that are useful for us. And so, for example, B has certain properties that allow one to show that this equation is at least locally well posed, say for smooth theta. It doesn't have to be smooth. This is foundational work going back to Kawashima in particular and Shizuta, who considered more general expressions like this and identified various abstract properties of the diffusion matrix which permit degeneracy. That's the main point that makes this a non-trivial statement. If this is a strictly positive definite matrix, then the local well-posedness of this equation follows from very standard techniques. But when you have some degeneracy, what you really have is a coupled system, one of which is purely hyperbolic, the first component, and the other components have some parabolic character to them. And the local well-posedness of that coupled system is much more subtle. It does require some additional properties of B. For example, it helps for the kernel of B to be constant, independent of C, and that's actually the case here. But so there are some abstract properties you can write down for this diffusion matrix that permit it to be degenerate, but that will give you local well-posedness. And so I'll be kind of assuming that, and I won't dwell too much on exactly what those properties are. Hopefully it's kind of plausible from our physical experience that this viscous conservation law should be at least locally well posed. I want to point out that it's also not clear that it's globally well posed. For example, because you have this this hyperbolic term here, which, for all we know, could just go off and happily form its own shock and just ignore the diffusive character from the other terms. That doesn't quite happen, but it's something that one have to be aware of. So there are global well-posedness results for certain restrictions of this model. If you have just the 2x2 system, so if I drop the energy equation and you work with, no, that's sufficient. If you drop that energy equation, and I think maybe you need to assume a certain equation of state for P, then you can get global well-posedness in one dimension for this model. But in general, things can get a little bit dicey when you're trying to state a global result. And I will not be stating a global result, but I will be using some solutions of this equation. So from our perspective, actually the main feature of this diffusive equation that I want to use is I want the diffusion matrix, although it may be degenerate, I still want it to act non-trivially in the shocking component, in the component of the background inviscid problem that is forming a singularity. If it's degenerate in that component, then there might be no significant interaction between the parabolic aspect and the nonlinear shock forming character of the problem, and you would be in a very different setting. But it happens that for Navier-Stokes, although the first component of Navier-Stokes is degenerate, the shock forming aspect of Euler is not concentrated purely in the density component. It involves all the terms here. And therefore, one can check that the Navier-Stokes diffusion matrix does act non-trivially in the directions corresponding to right eigenvectors of the genuinely nonlinear characteristics for Euler. So the other condition I want to recall is that, so if R is the right eigenvector for our shocking eigenvalue, lambda, and again, when I refer to something as being shocking, I have in mind that the inviscid problem is developing a shock. Now I'm adding a small viscous perturbation, and I'm going to try to understand what happens there. And so when I add that small viscous perturbation, I want it to be non-trivial on the right eigenvector. So we're going to need R transpose B R to be not equal to 0, and actually because of the non-negative definiteness, it'll be strictly positive. And as I say, this is something that can be checked for Navier-Stokes. This is true for the particular fluid model we're studying. It is a bit tedious to check it explicitly. But it's true, and maybe not so surprising. And beside the local well-posedness of the equation, this is really the key thing that I'll need, and I won't really need much else from my diffusion matrix beyond this. And in particular, this allows, for degenerate diffusion matrices like the ones we find in the physical Navier-Stokes equations. So given these properties for a general nonlinear diffusive conservation law, the kind of big picture question I want to ask is, how does a small viscosity modify shock formation? In particular, as I study the lead up to that gradient catastrophe, how does the addition of a viscous term in the equation with a small coefficient modify the behavior? And for example, from a scalar perspective, we could expect that the addition of this diffusive term would be sufficient to prevent the gradient catastrophe itself from forming. And that'll be the case here. So by adding a small amount of diffusion, you will prevent the actual infinite gradient from forming, but you'll just get a large gradient that depends in some fashion on the smallness of the parameter nu, and that's something that, among other things, we would like to calculate. In other words, how much modification to that singularity forming process do we get when we add this small amount of regularization? So I'll use this notation, psi inv, to denote the inviscid problem, the shock forming background model, the inviscid solution. And I'll use psi or psi with a new superscript to denote the solution of this viscous problem. So we'll use that new when I want to emphasize that dependence, but implicitly, if I write psi, I'm thinking of it as solving the equation over there, and therefore it's implicitly parameterized by the small parameter nu. Okay, so we have this model, theta bar, that I've said describes the behavior of the inviscid solution close to shock formation. And the first thing I want to calculate is how close can I get to that gradient catastrophe before theta bar ceases to be a good model when I try to plug it into my viscous problem. And the way I'll approach that is I'll plug theta bar into my viscous model, and I'll ask, how close do I have to be to that gradient catastrophe before the second derivatives on the right side start to overwhelm the first derivatives on the left? Because, of course, if I get too close and I have these super large derivatives, the second derivative is going to be massive. It doesn't matter how small nu is, eventually this is going to be much larger than the advection, and the diffusion is going to basically take over the behavior of the equation. And it's going to render this specific pointwise model relatively inaccurate. But on the other hand, if I'm far away from that gradient catastrophe, then my derivatives are relatively small, and therefore this second derivative will be beaten by the smallness of the parameter nu, and I should expect the right side to be perturbative. So there should be some transition between the two behaviors, and I'd like to know the threshold for that transition. So let's see, how should I write this out? Okay, so we're going to use theta bar as a proxy for the inviscid problem. We're basically focusing solely on the shocking component of psi, with the understanding that the other components are more regular, and so they're probably not going to play as big a role in this analysis. And I basically want to project this vector valued equation down onto that shocking component, and then think about the relative role of the advection and the diffusion. So let's write just for some notation, I'm going to use the letters sigma and omega to denote the shocking and non-shocking components. Sigma for shocking, omega for something else, I don't know. And I'm basically projecting, and so I've sort of chosen to rearrange my state space kind of arbitrarily so that the shocking component is like in the first coordinate direction of my space, just to simplify the notation here. So then if I want to project onto that first coordinate, I'm just going to be taking the like the 1, 1 coefficient of this matrix, the upper left coefficient. And again, this is achieved after some linear transformation of the state space that brings the shocking eigenvector into the first elementary vector. So there, I need to tell you what the advection matrix is doing in that 1, 1 component, and I need to tell you what the diffusion matrix is doing. So the 1, 1 component of the advection matrix, after all the normalizations I made last time, which included a Galilean change to shift into a frame that's moving at the same speed as the incipient shock, this matrix should vanish at the origin, or this matrix entry should vanish at the origin. And more generally, it should basically be proportional to theta bar, with the proportionality constant given by, well, one way I was writing it earlier was a prime of 0, but really this constant c is positive, and it reflects the genuine nonlinearity condition. And similarly, by this assumption over here, that B acts non-trivially on the right eigenvector corresponding to our shocking characteristic, B11, the action of the diffusion in this shocking coordinate, is some positive number close to the origin, or a positive quantity close to the origin, bounded away from 0. So to balance the advection term with the diffusion term,
This is for any side or any other side?
this is only for psi that is forming a non-degenerate. In the inviscid problem is forming a non-degenerate cubic shock. Yeah, in a genuinely nonlinear characteristic. And I'm assuming I've made all those Galilean transformations to kind of shift things to a simpler setting where all the bad behavior is happening at the origin. So after all of this, my assertion is that the advection term is going to be like theta times the derivative of theta, or theta bar. And I'm trying to ask when this is comparable to the diffusion. So on the right side, I'm going to have nu times the derivative of B11 at leading order evaluated at 0, because I'm thinking of this behavior close to the origin. So actually I can pull that B11 out. It's just a positive constant like C. So I'll really ignore their values and just focus on kind of a dimensional analysis of trying to balance these expressions. And I'm going to think about the spatial question first, namely, if I'm at the moment of shock formation, how close from either side spatially to the gradient catastrophe do I have to get before the diffusion is going to beat the advection? And so let me ignore the time piece of our cubic for a moment and just pretend that theta bar is just x to the 1/3, roughly speaking. So let's say theta bar is x to the 1/3. It's a simplification that will give the right answer. And if I plug that in here, so I just need to keep track of my exponents. And I'll pull this board up in a second. I remembered that I'm getting a little low here. So I'll have x to the 1/3, x to the minus 2/3, and that should balance nu times 2 derivatives of x to the 1/3, which will give me x to the minus 5/3. And I can collect all my powers of x on one side, and I'll find x to the 4/3 should be equal to nu. And solving for x, I'll get this expression that x should be of order nu to the 3/4. And this at least has kind of the right behavior. As nu gets small, it's telling us that we can get closer and closer to the gradient catastrophe before the diffusion starts to take over and beat the advection, and that makes sense. So one way of thinking about this is that we should think of theta bar and really of the full inviscid solution of the problem as being a pretty good model for the viscous behavior when you're outside this region. But when you're inside it, the diffusion is going to almost dominate the behavior, and you're going to need a different model to understand what's going on there. But at least it's a small region. And you can go through a similar calculation to understand how close in time do I have to be to the singularity before things start to go wrong. Because if I'm sufficiently far in the past, my inverse cubic is actually relatively regular everywhere. And so the diffusion will end up getting swamped by the advection due to the small coefficient of nu. So also, I only see a dominant diffusive character when I'm near the time of the gradient catastrophe. And to do that calculation, I basically want to use the heuristic that that x should be roughly like t times theta bar, and I can even replace theta bar by x to the 1/3. This is kind of abusive, but again, it'll give the right answer. That'll tell me that these things sort of are of comparable order in my cubic equation when t is like x to the 2/3. And if I bring that over here, then this would say that the diffusion should matter in addition when time is of order nu to the 3/4 raised to the 2/3, and that comes out to nu to the 1/2. So let me draw what I mean by this. So I'll draw a diagram of space-time. Here's space. Here's time. And what I've just calculated is that there's a certain anisotropic region in here, which is much larger in time than it is in space because nu is small. So a smaller exponent actually means a bigger number, something to bear in mind. So the scale here, I've zoomed way in so that the spatial scale here is nu to the 3/4, and the temporal scale is nu to the 1/2. And what I'm saying is that when you're outside this contour, roughly speaking, or well outside, a large multiple of it, let's say, the inviscid solution of Euler should give you a good approximate answer for the behavior of your actual viscous problem. But when you're inside this contour, you're sufficiently close to the origin where various derivatives are getting larger and larger, then inside this region, you have to take into account the diffusion here. You can't ignore it any longer because it becomes the dominant term in the equation. So diffusion wins in here, and everywhere else, just advection wins. And everywhere else, that should tell you that psi nu should be approximately given by psi inviscid, but this is not the case inside this region. And there's a bit of subtlety as to what I mean there, because both of these quantities will be quite small in this region. But what I have in mind is that, say, the ratio between them is going to diverge from 1 inside this region, but will be very close to 1 outside the region. Maybe it's worth writing down how big these quantities should be inside the region. So how large is sigma in particular, the shocking component, which is the one that I'm really implicitly analyzing here. So I guess I can carry it out here. That's just the same as saying how big is theta bar when these conditions are satisfied. And if I think that theta bar is the cube root of x, I should just take the cube root of this quantity. So throughout here, we should think that sigma, which is similar to theta bar, should be of order nu to the 1/4 in this region. So that's just the scale of our shocking component in this region. The non-shocking component will be something like the square of this, at least, so much smaller. Okay, so what do I want to do with these kind of informally derived exponents? My intent is to rectify the poor description of the viscous solution in this inner region. And I'm going to use these scaling exponents to do that. So I'm going to perform a blow-up analysis. I'm going to zoom in space and time anisotropically using these different exponents so that what is a very small region in the original coordinates becomes order 1 in both time and space after a blow-up. And I want to think about the equation, the Navier-Stokes equation, after that blow-up to see what has changed. So I'll introduce these blown up coordinates. I think I'll often refer to them as inner coordinates. So I'm rescaling time by nu to the 1/2, space by nu to the 3/4. And I need to blow up my solution as well, otherwise I won't see anything. So I'll have a capital psi, which is nu to the -1/4 of little psi. And I want to rewrite the Navier-Stokes equations in these new blown up coordinates. So I basically replace all the expressions here by their blown up versions, and I need to track all the powers of nu that I get, and then try to understand, try to cancel as much nasty polynomial nu's as I can, and try to get some sensible equation at the end of the day. And one thing to point out is that when I make this rescaling, when I blow up psi by a factor of nu to the 1/4, I'll pick out the shocking component, but the non-shocking one is going to go to 0 under that scaling because it's even smaller. So I should expect this psi at leading order to be dominated just by its shocking component. So I'll also introduce a bit of notation for that. So using my capital letter convention, capital psi is going to be decomposed into a shocking component and a bunch of non-shocking components, omega, and these are all going to be smaller. So we should expect that after this transformation, sigma is order 1, but omega is order nu to the 1/4. So at leading order, I'm just going to see sigma. So after I perform this rescaling, maybe I'll do it over here. So the rescaled Navier-Stokes equations I get.
Sorry, so the non-shocking components scale like a half?
Yes. Yeah. Because roughly speaking, they're like a square of the shocking components. Yeah. And this again, this has to do with a little bit of subtlety in how I'm measuring them, but we can talk later if we want to get into that. So I'm performing this blow up. Again, all I do is make a bunch of changes of variables and track the resulting coefficients in nu. And when the dust settles, this is what you're going to find. So the leading order equation is just going to be given by sigma, because like we were just saying, the non-shocking components are going to kind of drop into obscurity in this limit. And you're going to get, let me write it out a bit more carefully this time. You're going to get a derivative of the advection in the shocking direction. So A11 is the term of the advection matrix in the shocking direction, and I'm differentiating it to extract its leading order behavior, because at 0th order it vanishes. So this expression here is basically the leading order behavior of the advection. And then over on the right side, I'm going to get the diffusion in the 1,1 component, the shocking component. And I'll get error, which should formally at least be of size nu to the 1/4.
Just to be sure, this partial one is like d by d sigma.
Yes, it's like d by d sigma, exactly. And so, so that's a good way of thinking about it. So let me copy that. So this is like d by d sigma of A, which can be expressed as, it takes a little bit of linear algebra to check this, but you can show that at leading order, this is the same as the gradient of the shocking eigenvalue in its right eigenvector direction, which is exactly the quantity that is non-zero by genuine nonlinearity. And that makes sense because it's the coefficient of a nonlinear term here. So genuinely nonlinear means that coefficient is non-zero. So this is not just kind of some random derivative. This has deep significance in the context of the inviscid model. And this B11, the shocking component of the diffusion matrix is by hypothesis, as is the case in Navier-Stokes, it is strictly positive. So if I ignore the small error, what do I have here? I just have a scaled version of the viscous Burgers equation. Here we have the Burgers nonlinearity, and on the right side we have constant coefficient diffusion. And it's a scalar equation when I ignore the error, because I've reduced everything just to the leading behavior of the shocking component. So when you perform this transformation, when you perform this blow-up analysis, things simplify in the sense that you started with this complicated 3x3 degenerate diffusion model, but when you perform this blow-up analysis, at a formal level, you just get scalar viscous Burgers, a very, very well understood viscous conservation law that actually is explicitly solvable through the Cole-Hop transformation, if that's what you're interested in doing. So this is kind of a major advantage of this perspective. Now, of course, a bunch of analysis has to go into showing that the errors are actually small here, so this is a good approximation, but that can be done. So the main takeaway I want to make from performing this transformation is that you observe viscous Burgers at leading order.
I just want this showing this is all derivative in the quarter. That's when the derivative falls on B, right?
Oh yeah. Well, there's lots of contributions to that. So, for example, there's all the cross terms. There's all the non-shocking parts of the problem would end up at least of this size.
But the non-shocking ones you said were like needed at half.
They are, but one thing I've done was rescaled all my equations by a factor of nu to the -1/4, and that cancels out in a way that I'm sweeping under the rug. Yeah. But you're right. You would also get terms that come from derivatives landing on B, or more complicated expressions involving the advection. All of that would show up if you tried to expand this out more completely. Which we had to do in the paper, in fact. Okay. So the next question is, let's assume this is a good model. So let's assume that close to shock formation, when you add your viscosity, you're dominated by viscous Burgers after this rescaling. What I want to ask is, what solution of viscous Burgers do you look like? Because there are many solutions. And it's a bit of a funny problem because the region we're studying, this one here, is far away from where we're posing the initial conditions of the problem. We pose the initial conditions for the problem way down here at some fixed negative time t. This is a little region way in the interior of our domain. So I don't sort of explicitly know the boundary conditions or the initial conditions, if you like, for solving viscous Burgers in this region. It's somehow implicitly determined by the behavior of the solution, not by explicit initial conditions. But luckily, there are some things we can say about that. So which solution? One thing I should expect is that if I go further and further away from this region, say in the past, I should enter a regime where the advection is beating the diffusion, and therefore your solution should come to resemble the inviscid behavior. And at leading order, for the shocking component that we're studying, that should look like theta bar. Now, when I carry out that process, when I say I'm moving further and further away from the green zone, what that means is that in the rescaled coordinates, I'm sending capital T, my rescaled time, to past infinity. Because I'm, let's say this location is like capital T equals 1. Then down here is capital T equals 2, and I'm moving further and further away. I should say -1, sorry, to past infinity here. So as capital T goes to -infinity, sigma should resemble a rescaling of theta bar. We could think of this as a matching condition if we like. We're trying to match the inviscid or the approximately inviscid behavior in the exterior of this region with a solution of viscous Burgers in the interior. And fortunately, it turns out there's a distinguished solution of viscous Burgers that agrees with this cubic sort of to the highest possible order. So I'll be a bit hand wavy with how I state this exactly. But it turns out there's a distinguished solution that I'll call sigma hat of that viscous Burgers equation. That best resembles theta bar properly rescaled as t goes to negative infinity. And what I mean by that is, so you're looking for solutions of viscous Burgers that look like theta bar at past infinity, and there's so we're looking for an ancient solution of viscous Burgers that exists all the way into the past, and moreover, in the past, it has a certain profile. It's kind of like a scattering problem, although it's a bit funny to do that in the context of a viscous equation. But there it is. You're trying to find a solution that originated far in the past and had a given structure there. And there's a very natural way of trying to go about constructing a solution like that. You solve viscous Burgers using data coming from theta bar at an earlier time. And you just try to take some subsequential limit of these solutions as your initialization tends to past infinity, and you hope that it converges. And it will converge. And you can track how quickly the resulting solution, sigma hat, converges to theta bar as you go into the past. And you'll find that there's a whole family of solutions that all converge in some sense to theta bar, but one of them converges faster than all the others. And it's the one that we just constructed by initializing earlier and earlier using theta bar. So that's what I mean, that there's a unique solution that best resembles theta bar. There are other solutions that converge, but not as quickly. So this is kind of the best choice that we could make for a guess for what's going on in this green region here. So let me put it like this. If I take sigma hat, which is defined in the inner variables, and I blow it down, so I rescale it back into the original coordinates, little t and little x. So rescaling this function to a little sigma hat of little t and little x. The hope, the expectation is that psi nu is going to be approximately given by sigma hat and 0, at least to leading order, close to the shock. And I could be a little bit more precise. I could put in error of size nu to the 1/2 that I'm not tracking here. And this should be true in the inner zone. So in this green region, where before I didn't have a good pointwise description of my solution. Where does this come from? This would come from for example, from the non-shocking components that I've neglected in this analysis. And the discrepancy between nu to the 1/4 over there and nu to the 1/2 is because I also make a rescaling of nu to the 1/4 to go from the outer to the inner mode. Yeah. And for example, in this inner zone, sigma hat itself is actually of size nu to the 1/4. Yeah. But the main thing I want to get across is that this should be a better description of psi nu than just the inviscid model, because now we've accounted for viscous effects close to the origin. And the degree of error is lower than you would see without making that correction.
Sorry, just to be clear, you want to find a viscous solution that sort of is close to the inviscid solution in the parabola.
Mm-hmm.
And to do this, you found a solution that to viscous burgers that looks like theta hat away from the parabola.
So I don't expect the inviscid behavior inside the parabola to be an appropriate model.
Right.
I'm trying to correct it and replace it by a viscous behavior. But I'm saying that, say out here, the inviscid model should be a perfectly good description. And so I should use that to kind of initialize or to provide, say, boundary conditions for the viscous behavior inside the region. Does that make sense?
But you have to solve these as a system, right? You solve for sigma hat. So that's scaled of your Stokes equation.
Mm-hmm.
You also have to solve it for the annoying non-shocking ones as well.
Yes.
At the same time.
Well, so I guess what I'm arguing is that because the non-shocking components are significantly smaller in this region, if I just want to achieve error, say, of this size, I can forget about them and just treat the shocking component. Now, if I want a better approximation, I can delve into the structure of this, and I can solve some diffusively motivated problems for the non-shocking things. Yeah, it's a choice. But it's a choice that reflects an important feature of the problem, which is that when you're close to shock formation, your structure is dominated by a shocking component, which is partially decoupling from the non-shocking components. And that allows us to solve a scalar equation to get a good approximation of the system of equations, which is a big win. Okay, so let me write down a theorem that is true that is sort of motivated by the various expectations that I've written down on several boards here. That's kind of the big thing that we would be trying to show, given all this analysis.
The solution to that viscous burgers you get from Cole-Hop?
You don't need Cole-Hop to construct it, although there is a very nice Cole-Hop representation of it, kind of after the fact. But you can construct it using any number of convenient kind of PDE tools. I mean, viscous burgers is very nice to work with. So you could use energy methods, you could use maximum principles to construct a good ancient solution here. Yeah. So the point of all this buildup is to get a good pointwise description of the solution to Navier-Stokes with small viscosity. So let me state some consequences that would follow if we really carried out the analysis that I kind of started to a great degree. So I want a pointwise description of my problem. So let me start off by recording an estimate for the error in approximating the viscous problem by the inviscid problem. So this is the vanishing viscosity rate measured in L infinity. And I'm measuring it on the strip that starts at my negative initial time, which I've kind of neglected to talk about, but I'm initializing my problem at some past time, t naught. Then I'm running until time 0, when the inviscid problem would develop a gradient catastrophe. And I'm going to take the L infinity norm over all those past times and over everything in space. And I'm going to ask, what's the discrepancy between the viscous problem and the inviscid problem? And the answer is roughly on the board. If you make this approximation, this approximation is not accounting for the additional refinement that I just made. It's not accounting for the viscous Berger structure in the interior. It's forgetting about that, and it's just approximating the viscous problem by the inviscid dynamics. So when you're in this little parabolic region, the error you make with this approximation should be basically as large as the solution is in that region, which is nu to the 1/4. So the vanishing viscosity rate in L infinity in the vicinity of gradient blowup is bounded from above by nu to the 1/4, and it's also bounded from below by a factor of nu to the 1/4, because we haven't accounted for the diffusive behavior in the inner zone in this difference. So this is actually the sharp vanishing viscosity rate. And that will follow from the kind of complete analysis contained in our paper. So on the other hand, if we splice the inviscid model in the outer region, outside that kind of parabolic zone, and in the inner region, we use this this variation that is incorporating viscous information, sigma hat, and let's say that I'm still lazy and I still drop the non-shocking components. So in the inner region. So by splicing, I have in mind, like, you set up some partition of unity that selects the inviscid problem away from that region and the viscous model inside the region. So if we splice these two together to form a better approximation, call it psi app, then we improve this rate of convergence. Then the error is going to be of order nu to the 1/2 instead. And again, because of how the exponents work, nu is small, so this is much smaller than that. So this is one way of saying that all of these shenanigans involving viscous Bergers are actually worth it. They refine the degree of approximation by gaining you an additional factor of nu to the 1/4 when you use that extra viscous information in the inner zone. And basically a consequence of this as well is that if we blow up, so we zoom in using the inner coordinate change up there, and I look at capital psi nu, this is going to converge to capital sigma 0 locally uniformly in the inner coordinates, as all of this is true as nu goes to 0, I should say. So in other words, this formal analysis is actually real. It's getting at the real behavior, and that when you perform this blow up, you can rigorously show that under this scaling, you're converging to this special solution of viscous Burgers in the shocking component, and the other components, being of order nu to the 1/4 after scaling, are going to drop out in that limit, as stated here. Something I like about this is if I think about this unique solution, sigma hat, to viscous Burgers, it's being selected by the properties of theta bar. And let me recall theta bar somewhere up here, let's say. So actually, I can be more specific now. This is that same genuinely nonlinear coefficient that appears in viscous Burgers. And then we'll have minus beta times theta bar cubed. And beta depends on the data. It's this single real parameter which is governing the stretch of the cubic at the blow up time, at the gradient catastrophe. So my point here is that the only way in which the initial condition enters into this asymptotic is through the single scalar beta that governs the stretchiness of the cubic. All the other infinitely many degrees of freedom in the initial data get washed out when you perform this blow up. And so we're really observing a universal behavior here, which is parameterized by a one parameter family coming from the initial condition, but it forgets about everything else associated to the initial condition. Except for that one scalar, sigma hat is independent of the data, is what I'm saying. So this is a universal viscous shock formation profile that shows up kind of no matter what you do. It was actually something that Sanchit and I identified for viscous Burgers first. So we carried this analysis out for the scalar problem first. And we figured on just formal grounds that it should also arise in the system setting. And this is something that we have now confirmed with John.
Do you have the explicit dependence of sigma hat on data?
Yeah. If that's something where the Cole-Hopf representation really comes in handy. So I'm afraid I didn't write it down in my notes, but I can track it down in our Burgers paper for you afterward. But you can express sigma hat as a ratio of these big integral expressions, and the integrals just have like beta in certain exponents showing up. So it's a very explicit thing there. Yeah. And actually, it turns out I learned this recently. It turns out that physicists wrote down these integrals ages ago. So this expression arose in the physics literature like decades in the past, but some of the connections sort of weren't fully recognized. Yeah, there's another kind of small subtlety I want to point out before jumping into a few comments about how to actually prove this. One other aspect of the result is that the solution of viscous of the Navier-Stokes equations actually exists all the way up to time 0. And as I mentioned, this is not trivial because there's no general global well-posedness result that I know of for diffusive systems of this generality, and not for the 3×3 Navier-Stokes equation either. So you can't take for granted that there even is a solution up to this time. So what we show is that, well, the inviscid problem has a solution up to this time, and except at that very final time, it's regular. So up until that very final time, you should certainly expect that a viscous perturbation of it should probably exist, at least for small nu. And then we can show that you can actually kind of push through and continue the existence of the viscous problem all the way up to the time 0 when the inviscid background is becoming singular. So implicit in this result is also a statement that psi nu exists over this interval, at least for sufficiently small nu. So one of the funny things is that we don't prove existence for larger values of the diffusivity, which would presumably be better behaved because the parabolic action would be stronger. But the analysis we carry out does guarantee that there exists a solution of Navier-Stokes for small nu up to the time of gradient catastrophe in the inviscid problem. Is that a question? Yeah. This one too, yeah. There will be a lower bound, yeah. So this is also sharp, and I'll say a bit more about that in a moment. Yeah, thanks. Okay, so I want to say some things about how to prove the results here. So I've kind of set up, a formal asymptotic framework that would suggest that maybe these results are true, but it's by no means simple to take that framework and convert it into a theorem like this. So what are some things that go into that? So the most direct approach is to say, well, we just constructed what we believe is a good approximate solution of the problem. We took the inviscid model away from the singularity, and we modified it close to the singularity using this kind of universal viscous shock formation profile, sigma hat. So this is just a function. We could plug this function into our equation, and you would get a little bit of error because it's not an exact solution to Navier-Stokes, but it should be close if we've done our job properly. And you could try to argue that if you look at the equation for the difference here, that it solves basically a roughly linearized version of Navier-Stokes with a small forcing. And hopefully you could show that solving that evolution equation with small forcing and starting from 0 data keeps everything small. But that's just a hope. It's not so easy to put that into practice, among other things, because each of these terms have gradients that are either going to infinity or actually not quite going to infinity, but are becoming very large as functions of nu. So there's these large gradients showing up, which then means that certain terms in the equation are becoming pointwise large, but in small space-time regions. And it becomes very difficult to show that the smallness of the forcing actually leads to smallness of this difference. The basic point is that, at least in any analysis that we could cook up, we end up losing factors of nu when we carry out this analysis. For one thing, we're kind of splicing a hyperbolic problem in the exterior of a region with a parabolic problem near the origin. And going from one to the other, there's a little bit of friction there. And when we try to nail everything down using Sobolev estimates and things like that, we end up losing inverse factors of nu, which is bad. So for example, I think if we just carry out our naive analysis using this approximation, we're going to end up proving a pointwise error that's maybe like nu to the -3 or something, nu to the -2, which is terrible, because this should be small, and instead, after we lose a bunch of factors of nu, it looks like the error is large instead. So the way we got around this was we said, well, it's okay if we lose some factors of nu if the error here were significantly better. If this were a really large power of nu, we could lose a few powers of nu and we would still get a small number here. But it's not. There's a fixed limit to how good this approximation can be, because we dumped a bunch of the information of the problem. Like we ignored the non-shocking components in the inner zone, for example. So to handle the loss, one way to put it is the loss of derivatives in our analysis, we need a more accurate expansion. We need a more accurate description of nu that is accurate not just to order nu to the 1/2, but really to, ideally, to any power of nu that we would like. So to get this theorem, we're basically going to expand the solution to many degrees of accuracy further than seem necessary for these statements, but then we're going to lose a bunch of factors of nu in our analysis, and at the end it's going to still give us the result we want. So to overcome a loss of derivatives, which is the same as the loss of powers of nu to the -1, we want to approximate psi nu to order, say, nu to the 100. And if you're going to try to do that, you may as well try to approximate it to any order that you'd want. It's not going to save you really much any more work. But the idea is, if we could get a very accurate approximation like that, then we could lose, well, 99 factors of nu, and that would be okay. So how are we going to do this? How do we get a more accurate approximation? So in the outer region, where the viscosity should be perturbative, we can use a traditional asymptotic expansion for psi. So we just say, well, we have this, this viscous conservation law. It has a small parameter in it. So let's expand our solution in powers of nu and call that an approximation. So here we'll say that psi nu is given by the inviscid background at leading order plus a bunch of correctors associated to ever higher powers of nu. And there's a traditional machinery for getting at these correctors. You plug this formal power series into your equation. You collect terms that appear with the same power of nu. These give you evolution equations for the correctors and allow you to pin down their values by solving some PDEs, which turn out to be linear because you're basically linearizing around the inviscid background. So that's fine, but we should not expect that to give a good answer inside this green region. There, on the other hand, we know what we should do. We should switch to the inner coordinates and we should expand there instead. And we'll get some viscous problems there. And there we have powers of nu to the quarter showing up, which reflects the intrinsic scaling present. So in the inner region, I'm going to do something similar, but I'm just going to expand with respect to nu to the quarter instead. So after switching to inner variables, I want to say that my inner expansion should be given by this leading order behavior that I already identified, which is just that special solution to viscous burgers. And then at higher orders, we should have powers of nu to the quarter times some other correctors. And you can carry out a similar procedure. You're taking this equation, now including the error terms, you're linearizing around the leading order behavior, and you're trying to get equations for the correctors. You solve those equations, and you hope that you have a good description of what's going on. And you face a similar sort of problem when it comes to working with the inner region, which is where does the data for the correctors come from? Because it doesn't come from the initial data. It has to somehow implicitly come from the behavior of the solution, say, on the boundary of this region, roughly speaking. So the data for these correctors has to come from the behavior of the outer expansion on some intermediate contour. One way to put that is we're basically trying to match the behavior of the inner region to the behavior of the outer region, because these should be coherent descriptions of the same underlying function. So just to use more traditional language, we're developing a matched asymptotic expansion here. And a lot of the difficulty comes in making sure that the matching goes off without a hitch. Now, I want to mention that we're hardly the first to take a matched asymptotic expansion approach to problems of this sort, to vanishing viscosity problems. So this really goes back to Goodman and Shin, who tackled the same kind of problem, but when your inviscid profile starts with a fully developed shock, so when it has a full discontinuity. And then you want to understand, how does the viscosity smooth out that discontinuity in a very precise way. So Goodman and Shin developed a whole asymptotic framework for treating that. They had to use a different scaling for their inner problem. It ended up looking quite different than ours, but we're definitely drawing philosophically from that work. And of course, I also want to mention that in higher dimensions, Kevin has some awesome work in the same direction, performing these expansions around fully developed shocks satisfying the MIDA condition. That's joint work with Guess, Metivier, and Williams, several papers in that direction. So all of that treats a scenario where you already have a fully developed shock. And in some sense, what we're trying to do here is complement that by showing how those expansions might arise through the process of forming a new shock spontaneously in the interior of your material.
What's the rate of convergence?
So I guess there are several important differences. Let's see. Let me write that up here. So because they're approximating a problem that has where the inviscid problem has a discontinuity, and they're approximating the solution by a smooth viscous function, there's no way that they can get L infinity estimates, because the L infinity estimates are just not true. You're not converging in L infinity, but you can write down estimates in basically any other LP space that you would want. I think they express their theorems in L1, which is a fairly natural space in a conservation law setting. But you can extract from their work estimates in all sorts of fun spaces. So what's going on in the work of Goodman and Shin in 1D, and then let me also mention the three-dimensional results of Kevin and co-authors. This is your inviscid background. And then your viscous solution should basically be some kind of smooth interpolation of this shock discontinuity. So the viscous problem, or the viscous solution, is going to look like something like this. And the width of the transition from one state to the other in the viscous problem is of order nu in this model. So their inner zone is spatially scaled by order nu. And actually, the time needs to be treated differently, because in this context, we're dynamically forming a shock where there was none before. And so time is playing kind of a big role and needs to be properly rescaled. In the setting here, time is sort of not playing as singular a role. And so you don't need to rescale time to treat this problem. But I guess I would say then you can sort of extrapolate from this behavior what various error estimates might look like, and how you could start adding higher, finer correctors to this behavior. Does that answer your question without answering your question? Okay. Any more questions? And please correct me if I'm mischaracterizing your work. Okay.
So there, the shock is part of the data for the inviscid. Right? It's already developed. You have the shock. Assume it exists for some time. Right?
Yeah. So
you could theoretically control the solution on the viscous solution on either side, pointwise. That's just a fixed curve in space-time, right?
Yeah. So do you mean that if you sort of bracket this off and look at the solution instead away from the discontinuity, yeah, there you can, so there you're basically in the analog of the outer zone, and you can use a traditional power series expansion and get a very good description. Yes, certainly.
It's only when you go through the shock that you don't
Exactly.
do,
Yeah, that's where you need to incorporate the intrinsic viscous behavior here. Yeah. And so you can imagine as well that there should be, you could write down an ODE that should be satisfied by, at leading order by this this jump, and that'll give you a good candidate basically for the version of the leading inner behavior, which will again have a so-called viscous shock profile to it instead of the thing that we're working with here. Yeah. Yeah, it's a good question. So not yet, but that's like, you know, top of mind for me. Yeah. Yeah, so that's it's sort of like we've worked out half of the transition up to t equals 0, and then you really want to see what happens next. What happens going from a very small, you know, going from a gradient catastrophe to a fully developed shock, and how does the viscosity kind of track through that whole process? I hope to say something a little bit in that direction at the end, just some speculative remarks. Okay, so I want to mention a couple difficulties with carrying out this program, with developing the outer and inner expansions. Actually, the outer expansion kind of writes itself. It's really matching the inner and the outer problem that gives us massive headaches and causes us to introduce actually a third expansion that's doubly indexed by both this parameter and this parameter, and is sort of valid in an intermediate region and allows you to paste the two together well. I'm not going to go through it. But I want to mention kind of the principal new difficulty that arises when you're studying a system of equations, as opposed to just studying burgers, just a scalar problem. And it's basically something that I've been kind of lying about in this picture when you think about what happens with the other components, the non-shocking components. So until now, I've swept them under the rug, but now if we're developing a more accurate expansion, we need to account for the behavior of those non-shocking components. And a beguiling feature of these components is that you know, they have a non-zero speed relative to the essentially zero speed of our shock development. And so on this picture, if I drew the characteristics of the non-shocking components, they would be coming in at a positive angle relative to this picture. So the non-shocking characteristics are basically sweeping through this diagram like this. And that has an important effect because if I consider the value of the solution here, it's going to know about the viscous perturbations that you make in the green region because the values in this green region affected the non-shocking component that ran through it and then dragged that information out over here. So this still, in a certain sense, feels the viscosity, even though our formal scalar calculation suggests that the viscosity should play no role, or a merely perturbative role here. So actually, I lied a little bit. If you want to develop this full expansion that includes the non-shocking components, you need to expand the region in which you're performing your inner analysis, so that one way to put it is so that it's causally closed from a hyperbolic perspective. This region was not causally closed from the perspective of the transverse characteristics. So we need to close things up. And so this actually, the green kind of tongue that I drew is not ultimately an appropriate region to carry out your inner expansion in. You need to stretch it out in the horizontal direction. So you really need to, let's see, where's another color? I'll use this. You really need to work in a box, let's say. doesn't have to be a box, could be some curved contour, but the main point is you need to expand it to a larger spatial scale, which is comparable to the temporal scale, because the transverse characteristics are basically going to mix time and space in an equal way, rather than the viscous or the zero speed shocking characteristic. So this is going to be scale nu to the 1/2 as well in space. So you need to work on a larger region that's causally closed, and you need to work with the equations satisfied by the non-shocking characteristics. And this causes various technical difficulties in the analysis that I won't elaborate upon. But basically, when I started the work, I thought, oh, I've done burgers, so I know that this should be the region that you care about. And then we sort of quickly realized that there was this headache coming from these transverse characteristics, and it took a long time to work out the right kind of framework to use to account for this dragging of information out of the kind of intrinsically viscous region. But if you properly account for that, I guess the way I would sum up the procedure at the end is that once you've accounted for all the details, actually one comment that's worth making is that let's see here. If I take my Navier-Stokes equations and I perform this transformation, I wrote the equation for the shocking characteristic. It gave you viscous burgers. If I work with the non-shocking characteristics, if I try to look at their leading order behavior, what I'm going to find is that the advection term has just a straight up constant out in front. It's not vanishing at the origin because these characteristics will be transverse. They won't be aligned with the time coordinate here. So if it's over here, over here in this calculation, I won't have a factor of theta there. I'll just have a constant out in front. And what this is going to tell you is that actually the advection for the non-shocking characteristics always beats the diffusion for the non-shocking characteristics. The diffusion never plays a significant role in the behavior of the non-shocking characteristics. It's always perturbative in those components. So this is actually a simplification. When you go to write down equations for the non-shocking parts, those equations end up just being transport equations. They're not diffusive in character. The diffusion all comes as just perturbations. It doesn't kind of act at leading order in any region of space-time. So when you kind of account for that ultimately nice feature, you can say, what are the building blocks that go into this big family of expansions? What kind of equations do we need to solve to develop our approximate solution? And it's worth asking this because if you have to solve equations that are as complicated as the original equation, then there's no point in doing the expansion. So what kind of equations did we have to solve? So our building blocks for our expansion we can kind of go in order. So we had to solve an inviscid hyperbolic conservation law. Okay, there's no getting around that. That's just the background dynamics. We had to learn a bunch about that. That was the subject of the first lecture. So a hyperbolic conservation law, the inviscid dynamics. Then there's the correctors in the outer region, and these are not so bad. These are linear advection equations. No diffusion. And that goes into the outer correctors and the non-shocking inner correctors, the correctors for omega. Because as I just mentioned, the equations for the non-shocking components in the inner zone are just transport equations. So those are not too bad. Then moving to the inner expansion, we had to solve viscous burgers. But luckily, that was an analysis that Sanchit and I had carried out earlier. And then the remaining correctors here are linear advection diffusion equations. And they're scalar because the quote unquote hard equations to solve are the ones involving the shocking characteristic. And those just involve one component. So those are scalar advection diffusion, linear advection diffusion equations. And these are for the sigma correctors. The omega correctors for the non-shocking components are just transport equations. So the main point I want to make is that if you look through this list, everything has a significant simplification compared to the full viscous conservation law that we started with. Either we reduce it to a scalar problem, or we reduce it to a linear problem, or both of those things. And so this is kind of the point of carrying out the whole analysis, is that it's difficult to just directly work with the original problem and learn loads about it, because it's a complicated equation. But we've taken that complicated equation, and by extracting different asymptotic regimes, we've broken it down into a whole bunch of much simpler constituent parts. And we can analyze those constituent parts very explicitly, and then rewind everything and learn a whole bunch about the original problem. Any questions? Okay. So I wanted to finish by saying a bit about the crucial question that Kevin raised, which is how do you go beyond the gradient catastrophe? So what does that look like in space-time? And I guess I should say explicitly that everything until now that I've shared is rigorously pinned down in papers that are out on the archive, but the speculation that I'm going to go into now is either not written down or certainly hasn't been worked out in any rigorous detail. It's just kind of some formal ideas that are floating around in the ether. So this is speculation, not yet confirmed by any theorems, but definitely something we are thinking about. So I'm thinking about a situation where the inviscid problem forms a gradient catastrophe at the origin, a non-degenerate one. And what happens after? In the inviscid problem, what happens after is the shocking component, per its name, is going to develop a shock, an actual discontinuity. That cubic, if I push it forward to any positive time, is going to form a small but real discontinuity. And that discontinuity is going to grow in time until it's order 1. And this discontinuity, the shock, is going to emanate from the origin in space-time, and it's going to move at some non-linearly determined speed given by the Rankine-Ugonio conditions. So somewhere there's going to be a shock curve. And the corresponding size of the shock is going to grow from 0 at this location to a macroscopic size at a fixed positive future time. And actually, one can write down explicitly roughly how large it should be. The jump size should be of order. Off the top of my head, I believe it should be t to the 1/2, but I should probably double check that before being too confident about it. But the point is there's some positive power of t here that will give you the size of your jump that is growing from 0 at the origin to, again, something of fixed size later on. And the results that I mentioned over here, of Goodman and Chin in particular, since we're just working in 1D, those sort of kick in or start to become applicable after some fixed positive time. after the jump that you're working with is of order 1. So in this region, one can apply the results of Goodman and Chin. There's a small caveat that their results do still require the jump size to be small relative to other parameters in the problem. But anyway, there will at least be some window of time where you can apply the results. And what we've just done is we've worked out sort of everything that can be said about the solution in this region down here. And Goodman and Chin is applying up here. So there's a bit of a gap. And it would be nice to fill that gap. So it would be nice to have a uniform description of how shock formation, how the birth of a new discontinuity is modulated by a small amount of viscosity in some, again, uniform and new way. So I would put a question mark here, but say that this is work in progress. And the one kind of fun calculation I want to share with you that sort of suggests that the picture that we're working with here has some relevance for the picture afterward concerns the behavior of the inner solution. So the inner zone that I was talking about there in this kind of macroscopically scaled picture is a tiny little patch close to the origin. So I've just told you that in a little region here, that's where you look like sigma hat and 0 at leading order. And looking at this might suggest that if I continue to solve my viscous Burger's equation forward in capital T, maybe it will start to tell you something about how this new shock is being born out of the vacuum, out of nothing. Well, I shouldn't say the vacuum because we're working with gas dynamics, being born from a continuous profile. So there's two sides to this. So one is that if I'm working in this region shortly after a new jump is forming, close to the jump, so the jump is small, which means that it's spanning only a small range of state variables, psi. So at least if you're sufficiently close to the origin, but with positive time, you should still expect to reasonably approximate your Euler system by Burgers again, because your jump is only occupying a small region of space-time, and you can linearize Euler there and extract a Burgers model. So for small positive t, we expect a Burgers kind of shock to form, to be born here with the same characteristic size, I think t to the 1/2. And a viscous regularization of this in the spirit of Goodman and Chin, if I look at a jump for the Burgers equation and I approximate it by a viscous profile, you can work out the ODE that should be satisfied by that viscous shock profile, and you'll find that it's actually explicitly solvable for Burgers. And you're going to get a hyperbolic tangent. So let me say hyperbolic tangent of y, where y denotes some rescaled inner variable here. I'm not going to go too far into the exact scaling, accounting for the factors of t to the 1/2, and accounting for exactly how big y is relative to nu. Let me just say that the profile curve you get is given by hyperbolic tangent. That's the point that I want to get across. Okay, so this is just a fact that can be calculated from the Berger's ODE. On the other hand, we're working for small positive t, so there should be some kind of overlap where for small enough t, you should be in a region that is sort of accessible by this viscous approximation involving this special solution of viscous Bergers that I've talked about, this sigma hat thing, which was designed to have certain universal cubic scattering properties at past infinity. So on the other hand, we have this sigma hat to work with. So how does sigma hat behave? Now, as the time parameter, the inner time parameter goes to positive infinity, because that time parameter going to positive infinity would correspond to moving out of the origin toward macroscopic timescales. And this is where it really helps to have the Cole-Hopf transformation. So it is at this point that we make use of the Cole-Hopf transformation. And we say, well, there's actually an explicit representation formula for sigma in terms of certain integrals. And you can work out the behavior of sigma when you take this asymptotic limit. Capital T will appear as a parameter in those integrals. And you can formally send capital T to infinity and extract a limit. And you will get a hyperbolic tangent. So locally, uniformly, in capital X, you're going to get hyperbolic tangent emerging. So as I send capital T to infinity, this special viscous shock formation profile is settling down into the form of a kind of static viscous connection from one discontinuous value to another. And it's showing how you should kind of continuously emerge from the picture that we've developed here for past time into the future through the development of a new shock that is being modulated by some kind of viscous regularization. So this can't be a coincidence. And again, it points the way to a potential analysis along similar, although I think more elaborate lines that would potentially allow you to fill this gap. And it's something that we're actively working on. There are some interesting complications. So everything I've just discussed just pertains to the shocking characteristic. But as we keep bringing up time and again, there are these other characteristics out there that have to play some role. And they play kind of a complicated role in the inviscid problem. So when you have a system of equations like this, one of the components is developing a shock, and then transverse to this, there are other characteristics moving along that end up kind of running through the shock, and they also end up carrying away certain singular pieces of information from the moment of shock formation. So in a system, there are other singularities beyond the shock curve that get dragged out from the birth of the shock. These are called weak contact discontinuities. They're not as bad as shocks. They're not actual jumps, but they're locations of mere Holder regularity rather than smooth behavior. And they're being carried along the trajectories of the non-shocking characteristics. So a full description in this window would also necessarily have to track the evolution of and the origin of these weak contact discontinuities. And that's something that we haven't really grappled with yet. So that's kind of an existing puzzle that is not answered by this merely scalar analysis. So with that speculation, I'll wrap up. Thanks, everybody. Yeah, Benjamin?
I mean, I guess the question for both. So, do you guys think that you can use this kind of method to study some sort of vanishing viscosity limit for like 2D or 3D numbers of the Euler, in the sense that we know that 3D isotopic Euler is still closed, and this is done by Camilo de Levis and his collaborators. I forgot to collaborate with them. But I think after that, there's different groups that are trying to use vanishing viscosity methods. So basically, their this result is because your solution is never.
Is this a convex integration result?
Yes.
Yeah.
Yes, and there are different groups that are trying to combat this issue, and at least one group is trying to do this managing this viscosity thing. So basically, they're saying that in 2D and 3D, your Navier-Stokes doesn't have shocks. You don't have this global homogeneous problem, so you get the Navier-Stokes thing, and then you set the limit to zero. Do you guys think that your method can be used to do something?
Yes, we do, and actually, this is something that we're also in the process of writing up right now. I don't want to. I don't want to say that. I don't want to say yet that it works and that I can confirm everything, but it's something that we're working on. I would say that the question that we would be getting at has a bit of a different character, because we're examining this specific scenario where you start from smooth data and then you try to go through the formation of a single, birth of a single shock, which is a bit different than, say, trying to start from arbitrary, maybe L infinity data if you're being really ambitious, or arbitrary BV data or something, and then trying to get some selection principle. So I think in this context where you start from smooth data and then you form exactly one piece of nasty behavior, I think there already are kind of constructions of sort of what the candidate solution of Euler should be in this case, at least for short times. Actually, wait, no, there's not. This is what Chris Dula is working on, right? So maybe I don't know. I don't know exactly what state that's in, but anyway, it's not out in public yet. But there's believed to be a unique candidate solution for Euler in this case, a physical solution, and ideally, this vanishing viscosity approach would be able to identify that as the limit of a sequence of viscous approximations. But I guess the distinction I'm drawing is that at least it's sort of already clear on physical grounds in this scenario that there is a single solution that you're probably given by, and that this then kind of has a candidate limit that we could try to approach. I don't really think that this kind of approach would work for a more general problem of starting from kind of arbitrarily irregular data and trying to identify a unique solution. Mm-hmm.
So these weak discontinuities, do they show up when you try to do your expansion? Like, do they somehow arise before? Because our expansion is, for the moment confined to past times where these discontinuities have not yet formed. So the short answer is I don't know, but they must somehow show up. And I'm pretty curious to see, then you have to deal with how does the viscosity interact with these Holder curves, and it's not entirely clear at the moment, but somehow an analysis in this strip, I think, would have to grapple with that question. Yeah. Mm-hmm.
So if you look, in your figure on the far left of the report, in the differentiation region, actually you will have a green region size 2.
Yes. Yes.
And can you comment on how it interpolates and what the boundary of your region would be?
Yeah. Yeah, then it becomes smaller. Yeah. Yeah. So up here, you're right. So in here, there's kind of a whole. If you write out Goodman and Shin's work, you'll find that there's this whole green strip of width mu, which, as you observe, is smaller than, in terms of spatial extent, it's smaller than the width here. So I think what's happening is that when you have a fully developed shock, you have kind of a unit strength advection, a flow from both sides that is falling into the shock. And that is kind of compressing the size of the region where the viscosity is able to have any effect. Because if you go further beyond this, you're sort of getting swept toward the behavior of the shock. But as the strength of the jump gets smaller and smaller, the strength of the infalling flow gets weaker and weaker. And so I expect that what happens as you get closer and closer here is that basically you need to account an additional factor in front of nu that that would expand this region as the strength of the jump gets smaller. And I think that would give you an interpolation between this strip of size nu and the inner region of size nu to the 3/4 here. But it's not something that I've written down yet. Does that kind of get at it?
So just from the static shock.
Yeah. Yeah, so I think as the strength weakens, the viscous region sort of has a chance to expand a little bit. That's my guess for what's happening.
In the Goodman shed, the solution is point-line smooth from either side of the shock, right?
The inviscid solution.
The inviscid solution is
Yeah.
point-line smooth,
Yes.
right? And the reason that your viscous parabola is larger is because it has an infinite gradient, right?
Oh, yeah, that's that's also a good way of thinking of it.
So
Sure.
of course, there's no blowing up.
Yeah, I know what you mean. Yeah. The derivatives are uniformly bounded from both sides when you're up here. But then you
It should be much smaller.
get this cusp-like thing. Yeah, I mean, this was something that I found very interesting about the theory when I first came to it, because just completely naively, if you drop a viscous term into an equation and you ask, like, what's the spatial scale at which it should act, you would usually say it should act at scale root nu. That's just what kind of traditional dimensional analysis would tell you. And if you had a linear equation, that is the width over which you would be acting. But the nonlinear flow from both sides compresses the region over which the viscosity is sort of able to influence things. So the fact already that you have a nu here rather than a root nu, I mean, this is well understood going back to Khrushchev, but it's still an interesting aspect of the theory. And I think we're sort of running into some reflections of that. Anything else? Anything online? Doesn't look like. Should we wrap up?
Well, I think if there are any further questions, let's leave them for lunch. Thank you, Cole, for this amazing series of lectures.
Thank you all for your attention. My pleasure.